Good afternoon, everyone. I'm Maria Cristina Ceccarelli from the Smart Biointerfaces Group led by Professor Gianni Ciofani at Italian Institute of Technology. And our contribution in the framework of SPOC4 is related to develop a blood-brain barrier model with an embedded sensorization system. As many of you know, the BBB is a very selective barrier with a protective function with our central nervous systems, but at the same time, it poses also a big challenge for many therapeutic agents that struggle to pass through the BBB. So for this reason, to address this limitation, different models of the BBB were introduced, in vitro models such as transwell, but also in vivo model, the animal model. But they today often still are not so useful in order to predict the behavior of the BBB, and they are shortfall into the accuracy and into the translatability into the human physiology. So for this reason, today the most promising approach is the BBB on chip model, because they can take into account the flow, so to mimic the flow inside the device in terms of also of shear stress, but also in order to reproduce the cell arrangement, to induce the 3D cell arrangement. But how to monitor the BBB? Well, different strategies such as chopstick electrodes or metal wires were explored, but they are still not so useful because they can alter the flow, introducing some disruption, or they can compromise the sterile condition of the cells inside the device. So our proposal is to develop a BBB on chip with a sensorized systems in order to perform in real time and in a non-invasive way the evaluation of the BBB integrity and the maturation of the BBB. So the idea behind our device was basically to have two different compartments, a perfusion channel where we see the endothelium cells, the human endothelium cells, in order to have the flow directly in contact with the endothelium layer to mimic the shear stress, and in communication through a row of pillars with the brain compartment, where we recreated the three-dimensional brain parenchyma embedding the astrocytes and microglia in hydrogel matrix. For different kind of application can be used this kind of device. There is basically composed of PDMS microfluidic device and bonded on a glass substrate where we pattern the microelectrodes. Once we introduce inside the device the biological component, we started to characterize the BBB through the biological assay, the Levendad, to evaluate the conformation and the arrangement of the cells, such as the immunostaining to evaluate the expression of some specific tight junction, and also monitor, thanks to the electrodes, the BBB formation, as well as the permeability assay and evaluation of the drug crossing assessment. As you can appreciate from the confocal images, we were able to obtain in the blood side a vessel-like configuration of the endothelium cells in order to maintain the channel, let's say, free for the flow, to induce the flow condition inside the device. We also were able to obtain a 3D arrangement of the cells for the co-culture of astrocytes and microglia in the brain side. Then we evaluated the expression of one of the overexpressed tight junction in the human BBB, this DO1, and as you can see, the expression was quite relevant. Then, to monitor the BBB in non-invasive way, but just to measuring the electrochemical impedance spectroscopy, so the impedance, we were able to relate the increase of impedance to the formation of the BBB. And this data was confirmed with the permeability assay. So wholly performing the measurement, so without the imaging, without touch the cells, we were able to understand understand if the BBB was formed, and also to understand if the BBB was well formed. So we can distinguish between an homogeneous BBB and a not homogeneous BBB, just measuring through the microelectrode system. Then we also model an equivalent circuit in order to take into account each compound, the matrigel, the cells, and the media, to extract one of the most relevant parameters for the BBB, the trans endothelium electrical resistance, the TIA, and we were able to obtain a deviation between the experimental data and the fitted value thanks to the equivalent circuit less than 2%. Once we characterized the device, we tried also to induce inside the flow condition and to induce the shear stress in order to mimic the in vivo situation. We performed a simulation to identify, based on the geometry and the design of the device, the flow rate. Once we selected the flow rate, then we compared two different kind of drugs, chemotherapy drugs, the temozolomide, the most common drugs for brain cancer, and the doxorubicin. There is no specific for the brain disease. And we observed how we, thanks to the device, are able to obtain a similar trend that we have in vivo with a very high permeability of the temozolomide compared to the doxorubicin. Now we are currently working to replace the titanium platinum microelectrodes with graphene electrodes. But why the graphene? The graphene because it is characterized to have high optical transparency, and in terms of electronic and thermal conducibility, it is better than the platinum. So thanks to the combination of two different techniques, the wet transfer, we obtain the monolayer graphene on the glass substrate. Thanks to the techniques of chemical vapor deposition on the substrate of copper, we obtain the monolayer, and then it is transferred to the glass. Once we obtain the monolayer of graphene, then we are able to pattern the monolayer with traditional lithography, and we can obtain the design of the electrodes. We try to also to evaluate different kind of design to optimize the process and to see what could happen. So we first of all try to cover the platinum electrodes with graphene. Then we try to realize directly the sensing pad in graphene, and also in the third design, we try to realize in graphene not only the sensing pad, but also part of the track. And we characterize the monolayer graphene using the spectroscopy and the microscopy. Based on the Raman microscopy, we were able to appreciate the typical peaks of the CVD graphene monolayer, especially at 1,600 the G peak and at 2,700 the 2D peak. Then we evaluated also the conductivity of the graphene, and we observed how the device in which we have the electrodes coated with graphene, we have a better conductivity. So now we are try to realize again the BBB with different kind of electron inside the device, and we perform some preliminary tests to evaluate the biocompatibility and the adhesion of the endothelial cells, mainly on the graphene electrodes, and we obtain quite good results, but as you can see, because of the characteristic of the graphene, the hydrophobicity, basically, the cells are not able to attach without any coating. So we try to evaluate the fibronectin, and we observe that also with very low concentration of fibronectin, we are able to obtain a quite homogeneous layer of endothelial cells. So as the next step, we would like to use the device to test nanoparticles, because we are basically a lab in which we develop nanoparticles for cancer application, therapeutic agents. So we would like to test the permeability of this kind of nanoparticles and the passage through the BBB. So thanks to all my colleagues, and thank you for the attention.